Hi, everybody. Welcome back to seminar. So today I have the pleasure of introducing President Krish Sharman, who's the Endowed Chair in Renewable Energy and Professor in the Department of Mechanical and Industrial Engineering at the University of Massachusetts Amherst. He holds a PhD in naval architecture and marine engineering from the University of Michigan. He's been an academic at various universities in Australia and the US for the past 25 years. His areas of interest focus on design and fluid structure interaction, analysis of floating offshore wind systems, wave and tidal energy systems, coastal food production systems, and offshore platforms in general. Please welcome Professor Krish Sharman.
Thank you very much, Zach. And it's a great pleasure to be back here. I was just recalling with Martin and Diane that I was here January of 2020. A lot has changed since, right? And but it's nice to catch up with everyone and give an update on some of the research we are doing. And part of the reason why I went back that far was I wanted to look at my presentation then and make sure I'm not repeating the same thing in case somebody in the audience has very good memory. So today I'll look at covering three topical research areas in the mooring, in the broad sense of mooring. I'll talk about some of the research we did with floating wind applied to shallow water, and then look at some of the field measurements we did with an oyster farm that was slightly older than other research I'll show you, and then take that a bit further and talk about synthetic moorings and the numerical modeling of that. And then I'll wrap up with some of our current research that's happening in the area of mooring systems. So just as a way of introduction, when we think about mooring systems and why even worry about mooring systems for the blue economy, we need to go back and look at mooring systems for offshore platforms and ships and boats and others in general. We know about anchor, you drop an anchor line, and we also know about how mooring system works with oil and gas platforms. The basic understanding is very different from the way mooring systems work in blue economy systems. Now, one of the fundamental differences is when you have mooring systems in deep water, you really try to avoid mooring lines from kind of getting any sort of wave frequency. They are primarily designed for mean and slow drift motions. And consequently, the lines can be designed with a lot more leniency. And also, it's still common in the oil and gas industry to do decoupled analysis. You can do a mooring analysis separate from an entire platform dynamic analysis. So the platform becomes like an end condition to the mooring line, and you can do a complete mooring analysis, and the mooring still works well. It's very hard to do that for blue economy systems. So when we think about mooring material, we started looking at chain. That's where we started, right? And chains are still widely used everywhere. They are quite heavy, and they become quite expensive. And given that the blue economy industry is not as wealthy as the oil and gas industry, expensive part really kind of cuts in. So we got to think of alternative materials. Even in the oil and gas industry, chain was slowly taken over by steel wires. Also, since I would say, I recall the time when Petrobras in Brazil introduced synthetic moorings, that wasn't that long ago. Maybe about, I'm beginning to think, was it in the late 90s, sometime around that? Wasn't that long ago, 15, 20 years ago. Synthetic ropes made their way into permanent mooring systems for oil and gas, and they are very thick and very large rope systems. Now, when we think about blue economy systems, there are some new challenges. First of all, the layout is very complex, and the architecture can be very intricate. You have several string systems, several elements put together in a string, and you are holding them together by ropes. And then they could be subject to tidal variations and then shock loads because the string can move relative to one another. But ropes have been deployed in the fishing industry for years, for several years. So the experience is there. When we start thinking about blue economy systems, the difference is it's a larger area, right? And you're also worried about inspection and maintenance. So whatever we can do to reduce breakage and minimize damage would be very welcome from the point of view of inspection. So the operating costs is where the benefit of doing mooring system research really shows. Okay. With the floating offshore wind turbines, there's unique challenges in that the platforms are very light displacement. They are not as large and heavy as deep water oil and gas platforms. And you also have a very dynamic payload. And unlike oil and gas platforms, winching and tensioning equipment may not be readily available. So as lines, as you know, synthetic material kind of softens and it stretches over time, all those things, and you need to think about periodically winching and checking the tension on these lines. So those become challenging. And when you have 100 turbines, you can imagine the number of lines that have to be inspected. And there's also interesting challenges in shallow water in that catenary shapes will have a very long lay, and mooring is definitely affected by wave frequency loads, and that can affect the safety factor of these lines. And we also, in the past, did some work on shock loads, and I'm not covering that in this talk today. So I want to talk a little bit about this, how we can look at mooring system for a floating offshore wind turbine in shallow waters, particularly the US East Coast. This was work that was sponsored by the National Offshore Wind R&D Consortium, now RDC, that emanated out of New York, but it's a national agency supporting research in various topics. And I had a couple of PhD students, Samir Saleh and Ahmed Al-Shuaib, work on this project in collaboration with a number of people, Richard Akers from Maine Marine Composites, Banjun Koo, and Happy Lahio Mati, all from Technip Energies in Houston. Also HKIM, also from Technip Energies, Sanjay Arwadi and Matt Lackner from UMass Amherst. So we had an industry consortium collaboration from Houston, and we want to look at how our current state-of-the-art mooring analysis applies to floating wind turbine in shallow waters. So we did, this is basically a front-end engineering or a pre-front-end engineering study. And we did a literature review followed by some design basis, setting up a design basis and selecting a suitable mooring system, did some numerical simulation and did some cost modeling. So we chose a 10 megawatt reference turbine, which is an IEA reference turbine, 3 blades, upwind turbine for this analysis. And we chose 2 sites in the New England area, Monhegan in the Gulf of Maine, for which there is quite a, we have 3 years worth of environmental data from a humane buoy which was deployed there. Water depth is nominally about 100 meters. Okay? And then we chose another site off of Nantucket, where there is a NOAA buoy which has been producing data for a very long time. The water depth where the buoy is around 75 meters, 74 to be precise. But we we chose a water depth nearby, which is like about 60 meters, because we want to study how we can design a mooring system for 60 meters. As you know, 60 is very shallow for moorings. And so based on the buoy data, we were able to get the environmental parameters, the wave height period, the current speed, the wind speed. And we chose 3 load cases as specified by the American Bureau of Shipping. DLC stands for design load case, DLC. So design DLC 1.6 is the operating condition where the turbine is operating, producing power. DLC 6.1 is where there is some kind of a fault. So the turbine is sitting idle, but still we are in kind of the operating environmental range. And they're all designated by 50-year storm conditions. Okay, and then survival is SLC, survival load condition 1.1. The requirement is 500-year storm condition, as stipulated by ABS. So based on the buoy data and using certain forecasting and probability models, joint probability models, we had access to all this information, which we then used for the purpose of this project. So for those who are familiar and have been keeping track of the industry, there's a 3-column semi-submersible, which was designed for a code comparison exercise by the National Renewable Energy Labs. And we took that reference basic open source semi-submersible and then expanded it and increased the size upscaled it for the purpose of 10 megawatt and did the analysis with this one. The interesting thing is because of Technip's expertise with mooring systems for oil and gas and other commercial applications, we chose this hybrid system where you have many of the offshore mooring systems have 3 components. You have a chain in the upper part, a fairlead chain, and then you have the anchor chain, and you can have a steel wire or you can have a synthetic line in between. In this particular case, we went for a little bit more complex in that we added a heavy chain in the upper part and also moved the fairlead all the way to the top so that we'll have a lot more line length and make the whole system a little bit more catenary-like, bit more, bit softer than what we would normally have with this shallow water tank. So, and you can see some of the dimensions, the diameters of the lines we chose, quite large. But this is coming from the oil and gas industry, so there is a certain level of conservatism built into it. So with this system, and we tried multiple lines. We put 3 lines per corner, 2 lines and 1 line, and tried a number of combinations. And this is typically the numerical simulation strategy we would take. You have the hull model in a 3D CAD modeling system, and then you use some kind of hydrodynamic package. In this case, we use the software environment for a boundary element analysis, and then you get the coefficient file, and then you use that into a time domain mid-fidelity software like ArcaFlex, where you can do all the simulations. So these are some of the results we got after a number of simulations and all the validation. It's all published in one of the papers. I'm just showing you the results for the survival load case. And what you see on the left side is the line tension, maximum line tension. On the right side is a safety factor corresponding to that line tension as stipulated by ABS. So typically the American Bureau of Shipping, ABS, and most of the codes recommend a safety factor of 2.0 or higher. So with all our simulations, this is the survival load case, 500-year return period, pretty intense storm. We find the maximum line tension in the case of one line at 60 meters water depth, one line 100 meters water depth, and the blue corresponds to the wind turbine kind of oriented in the wind turbine always looks into the wind. So when the wind is in the same direction as the wave, the turbine is looking into the wind. And then you can look at the case where the waves are coming one side, the wind is coming from the other side, and the entire turbine is 180 degrees rotated. So it's opposing the wave direction. So those are the two extreme cases we looked at, shown by the blue and the orange bars. And you can see here, the maximum tension is around the 6,000 to 8,000 kilonewton range. And that gives a safety factor of a little over 2. So our conclusion was our current design philosophy, materials that's available, our mooring systems are actually okay to be used in shallow water. This was followed by a cost analysis, and certainly there's a way you can optimize the cost and shrink the size of the material. So some more optimization is definitely possible beyond this point, and given that it's a little conservative. But what was more surprising to us than the strength was the fatigue. So we did a very, very brief fatigue analysis because it was funding ran out, basically. So we took an exposure duration of 25 years. Sorry. Exposure duration of 25 years. But we extrapolated from some limited number of simulations, and we used the Arcaflex has some simplified ways of doing fatigue analysis. So we threw in 75% of the operating condition and 25% of system in downtime. So it's not producing power. And for fun's sake, we also threw in one of the survival conditions. And based on that, we looked at the number of hours, and then depending on the number of cycles of waves, you can do a count of how many times and what sort of load ranges the mooring line is subject to cyclical loads, and from there you can calculate a level of damage. The more proper way is to use a scatter diagram, and then you have different environmental conditions having different levels of probability, and that needs to be brought in when you do a proper fatigue analysis. But this one sufficed for the purpose of this project. And what is surprising in this study we found was the fatigue damage to the synthetic material was okay. But really what was failing were the chains. So that was very surprising to us. So the chain components will fail, are predicted to fail in the case which is most commonly used in offshore wind, which is just one line per corner. And as we know in the oil and gas industry, it's always multiple lines per corner for redundancy purposes. If you have one line failing, system will still be okay. This is an issue offshore wind is grappling with. Should we put multiple lines, or should we contend with one line per corner? And if a line fails, the entire thing will shift somewhere. Maybe that's okay. The power cable may suffer something as a consequence. So that is still the jury is out on that. So as you know, this industry is so young. It's still, a lot of these things are kind of being worked out. So this was a very interesting finding, and then we published, we completed this project. And hopefully there'll be some further work where we can do some more serious fatigue analysis of mooring systems for offshore wind. So I want to shift a little bit into topics which, Zach, you're interested in. Oyster farm in inland waters. This was some work we did in Maine. And some of the pictures I'm going to show might be very familiar to you all. Dave, for sure, you would recognize this. These ones, the Moog farm, where we had the pleasure of working with their colleagues from Moog, including Jeff Auger, with whom we wrote the paper. And you can see strings of cages all put together with the lines. Various types of ropes are being used. Ropes are rarely tested. They just bought from your standard vendor. Oftentimes you don't know what sort of loads these lines go through. So what we did as part of some research is, this is a Moog farm, an aerial photo of it. And you can see some of the cages they use there. What we did as part of this work is to actually instrument these lines with the load cells and data acquisition systems. So these dashed lines here show 3 different deployments over a period of, now this is a few years back, so I'm guessing it's about 3 to 4 weeks. So we had one deployment after another. Actually, the first deployment failed right here. That's why we don't have any data on that. The second deployment actually worked fine. And then we put a third deployment in there. Interestingly, during one of those deployments, we had a huge gust of wind gust. And so we were able to capture the effect of wind gust, which kind of stood out. That you can see in here, there is a little bit of wind gust related things. But there is some data we put in there. This one definitely has some wind gust effect, but there is another data set which has a very prominent wind gust. What was very interesting was some of the loads we measured. The maximum loads we measured was the first time the people knew the actual in situ loads that were being experienced by the lines. They knew by experience what it should be, and they can just look at something and say it's gonna last or it's time to replace it. The intuition is great, but we have some engineering results after doing this. And what was, this is a gust episode I was talking about. What was very interesting for us, being scientific, looking at it scientifically, was you see these the red lines, which are basically tensions. So you can see the mooring tension, the data, the scale on the y-axis, and the orangish line is the mooring tension. And the black line indicates either the current or the tidal height. And what was very interesting to us was how the lines actually relax. You can see the viscoelastic nature of the lines here. The line basically stretches and tenses as the tide goes up. And then as the tide starts dropping, the line kind of relaxes, and then it's at a low tension for a while. Obviously, it's stretched already, and then it remains slack for a long time, and then it picks up. So this sort of time delayed behavior of the ropes was very interesting to us. And that's what one of my PhD students, she started looking at it more carefully. So from the study, working with Moog farms, we basically looked at the measured tensions, and that's actually in the paper that was published. From the measured tensions, we used simple Morrison's equation type formulation to actually come up with the upper bound and lower bound of tensions, and it actually agreed well with the field measurements. So it's a very interesting, simple tool we could use to study mooring lines in complex environments. But I wanted to spend a bit more time talking about the viscoelastic behavior of these lines. And knew him, Jessica, she did her PhD, and she started in Maine, moved with me to Massachusetts and completed her PhD there. And now she's She's working for San Diego National Labs, doing various interesting problems in renewable energy systems. So viscoelastic model. So as we saw in the previous graphs, what happens is the system is not just purely elastic, doesn't come back as quickly as it goes, but it actually relaxes. So if you hold the tension for a while, the system actually relaxes. And then the tension kind of flattens out. What you see in this graph is basically the strain versus time and how some of the elastic behavior is just happens almost instantaneously. Viscoelastic behavior takes time. So this time delay is what is not captured in existing mooring simulation models. And we were curious as to how viscoelastic and viscoplastic behavior affects mooring performance. I'm just going to talk about viscoelasticity in this talk, but Jessica's PhD work actually covers viscoplasticity. So just a couple of slides of math here. Now we know for a linear stress strain, tension is related to the strain, or the force is related to the strain through the Young's modulus. And when you take tension over area, you get the stress is directly related to the Young's to the strain, right? In viscoelastic models, this is the Shaperi's model published in 1969, still widely used. In a nonlinear viscoelastic model, you actually have the strain. So this epsilon sub VE for viscoelastic, the strain depends on the instantaneous compliance. And when you just look at this term here, so you have the strain and you have the stress, and so this D naught is actually the reciprocal of this Young's modulus. So that's the instantaneous compliance. So if you do not have any viscoelastic behavior, the strain and the stress are instantaneously interacting. But when you have viscoelastic nature, then you have this entire extra term, which is basically a transient thing, right? So just like you have instantaneous compliance, you also have a transient compliance, delta D, and that is a convolution. You have to convolve it with the history. So it's a history term, right? So the transient compliance, it's a convolution with a reduced time, which kind of tells you the nature of the rope. It's like an internal clock. That's what they call it. So the way the system responds in a viscoelastic manner is like all about the internal nature of the system itself. So in the case of a rope, it's the age of the rope, the material of the rope, how much heat is released due to hysteresis and stretching. All those things are captured in a very loose ad hoc manner through these coefficients G0, G1, and G2, which are usually found experimentally through rigorous step-by-step systematic experiments. Now, when we do experiments, when we do creep type experiments, we are usually subjecting the system to a load and we measure the strain. So what we really want is to find a way to capture the strain or the stress from the strain. So Jessica's work involved a numerical inversion scheme where you're measuring a strain and you have a target viscoelastic strain through the previous formulation, and then you define an error term, and the error is then a function of the strain itself, and the derivative is with respect to the stress. And so we then start looking at the ratio between the error and the rate at which the error changes, and then start correcting the stress from the original stress value corresponding to that strain. And this can be done in an iterative manner using whatever experimental data we have already. And then once we have that, from the stress, we can then calculate what the line tension would be for a given strain. So this was implemented in a code, and this code was then verified through or validated through a number of published experimental data sets. And here is one data set where there is a line, and the fair lead was sinusoidally moved, and the line tensions were measured through the experiments and published in 2016 by some authors. And so we took two of those cases for two different oscillation periods, two different oscillation amplitudes, and then looked at what the viscoelastic code gave in terms of results and what the experimental data also showed. So here you can see tension in the line as a function of time. Same thing for those two cases. And the black line is the experiment, and the red line is the simulation from the viscoelastic code. Reasonably satisfactory. There are clearly some variations, but there is quite a lot of empirical data that goes into these models. So I told Jessica, I'll be very happy if both the curves are in the same page. That's good enough for me. But she was able to work on it, get something really close. So very happy with that. We then moved on to a bunch of other things. So for example, hysteresis. Can we predict the amount of hysteresis in systems? So this is one example where you have a synthetic line, and there's an anchor, and the fair lead point is really moved left to right at some velocity v. So it's a loading and unloading going through at some velocity. So depending on the velocity, the nature of the material, the loading and unloading can have different curves. This is the stress, and you can see the time. And as you all know, the hysteresis loop tells you how much heat is released and the energy loss and all those things. So the data from Lai and Becker, which is a finite element model, they were able to get some data. And the blue curve is actually the result from our viscoelastic simulation. And again, the trend is captured quite well. We want to do a little bit more, and we actually wanted to apply it to the case of something more relevant to either offshore wind or some blue economy system. So we coupled it with this program called FAST. FAST is a National Renewable Energy Lab open source code for modeling wind turbines. Within FAST, actually FAST is an older version now. OpenFast is the newer version. And within OpenFast, there is a mooring module called Moordyne. And so the viscoelastic module was integrated into Moordyne. And we studied one particular case where we could capture the dynamic stiffness of these lines. So the fair lead was displaced to a mean load condition. So we produce an initial, we take the pre-tension and then add the mean tension to it. And then we exert it at 30 cycles with a constant motion amplitude and period. And we measure how much stress the line accumulates, and then, or the force. And then from the force and the motion amplitude, we can get the dynamic stiffness through this form. The interesting thing is with all these lines, depending on the mean load, the dynamic stiffness changes, right? So that's what we saw in the curves here. You can see this is the tension at the fair lead of this line versus time. The mean load is changed continuously. As we change the mean load, and these little black boxes here are basically 30 cycles of up and down motion. And it tells you how much tension is either required, how much force is required for this motion, or how much stress is accumulated in them. So based on the height of each of these black boxes, we can actually work out what the stiffness is at these locations. And then that's what we plot here, is the stiffness as a function of percentage of the mean breaking load. And that basically is the mean tension at each of these black locations. What you find here are these two graphs. One of them is for polyester, the blue is for polyester, and the red is for aramid. And the dots are basically experimental data from Davies et al. From 2002. So they obviously did for oil and gas applications, but the material using some of that data, our simulation gave results kind of similar. I was very excited when I saw that graph. Jessica wasn't. She said, "Oh, this doesn't look very good to me," because my simulation data goes this way, and whereas their field experimental data goes this way. But I see that this is like really close. And maybe I'm an optimist. But you see here, it's even better. Aramid is supposed to be even more difficult, but actually the results came out quite well. So I think I finally managed to convince Jessica that, okay, it's time you finish your PhD and you need to go gain employment. So I think she was happy to complete the work. But I was very impressed with the outcome from it. Clearly more work needs to be done, right? We all need our jobs. And so I need more money to continue this work. But there's plenty of very interesting outcome that came. So we have a number of ongoing projects, and it's when you prepare for seminars like these, you realize, okay, when you pull things together, you see, oh, there's all these common things binding all of them together. And in this case, our research on moorings goes into a number of these other topics. I'll show you some results on these three topics we are working on right now. The first one is the smart rope idea, which is a MIT Sea Grant funded project. And the idea is to integrate smart strand technology into a marine rope. This is done in collaboration with Microcorp, based just outside Boston. And what we are doing is we are taking some composite strands which are used for military and other applications, right? And that's like textile type material. And you see in the picture there, that's the thickness of a penny. And this is the strand. So that's how thin it is. So we are going to test it first. We have done some preliminary testing on it. It's some kind of a Dyneema composite yarn. We did some preliminary testing. We have done some tension versus strain instron type tests, but we are doing a lot more tests in water and outside water to see how well this one can, how the strength of these is. And then we want to integrate it into a rope and see if we can use it for condition monitoring of ropes or condition monitoring of net strands in a fish cage and things like that. So that it's a very preliminary study. And this is our wave current flume facility, which is now operating. And we plan to build a 2 degree of freedom system and put some kind of this type of strand underwater and then start oscillating it, just very similar to the viscoelastic type work I showed. And then we want to measure the strains and see how well we can predict it using different techniques and whatnot. So our research is still very much open at this point, but we are just starting that work. So that's very exciting and ongoing. Biofouling is another challenge. That's a biofouling in mooring lines and many structures used. Offshore wind is just getting to understanding this because everything is in 50 to 100 meters water. Sunlight penetration is there. So biofouling is definitely an issue. We have an ongoing collaboration with the NON, where they have lots of field data on biofouling. And right now I have a postdoc from NON, Dr. Maduka, who's been in our lab doing measurements on biofouling. What they have done in France is actually collect underwater images, and from the images actually develop a 3D model of mussels and then do 3D printing of mussels onto a cylinder element based on the most dominant roughness. And it's a 1-to-1 scale of the model, which was printed and then was brought to our lab, and we did experiments on it. So you can see a reference smooth cylinder model, and then this is the roughened biofouled model, both in the lab. We did tests with pure currents, with the waves, and then with waves and currents. So we have lots of data, which Maduka is analyzing. One thing was very interesting is in our film, we are getting a shear profile, which looks very interesting. So we think we might be able to get something useful out of doing this experiment. And you can see some range of KC numbers and Reynolds numbers and reduced velocity, which is waves and currents put together. So different current and waves conditions. So we are in the process of analyzing it, but I don't have any results to show. Do we have time to run a video?
How long is the video?
I'll skip it in case. I mean, it's just waves going fast. For some people, they love this.
Let's see waves.
You want to see waves? See? Diehards, we love waves. So let me see if I can move it up further. Yeah, there you go. So this has currents underneath, and you see a little distortion of the surface because of the currents. But you can see the wave and period, the wave amplitude and period, and a couple of probes which are vibrating a bit because of the waves. But and you have the cylinder right in the middle. So we have a 6-axis load cell to measure the loads on it. And now comes the job of extracting inertia and drag coefficients and trying to make sense out of it all. Okay, the last thing I want to mention is this hybrid mooring system idea in collaboration with UPM, University Polytechnical in Madrid. We have an exchange student, Tomas, who's been with us for a year. He's looking at hybrid mooring systems for a spar, floating offshore wind turbine. And a little shout out for a marine conference in Madrid in June this year. He has been looking at effect of clump weights on a mooring line and how they could change the behavior on the mooring line and how can we model it. There's still a lot of confusion about clump weights and how they affect the mooring line performance. And so he has a number of experimental data, experiments he did in Madrid. Now he's doing simulations and trying to make sense of the comparison. So hopefully in the future, I can talk a bit more about some of the results he got with and without clump weights. And have some papers coming out of it.
Well, now we have a couple minutes for questions, so please go ahead.
Yeah, hey, a very nice talk. A couple of questions about the first part. You showed that you had this heavy chain in the mooring system. Is that a way to shorten the overall catenary mooring systems in what is relatively shallow water floating wind turbines?
Yeah, actually, by using synthetic lines, we shortening the synthetic segment. We are shortening the lines quite a bit. But what we wanted to do was add a heavy chain in the top, so it will create a bit more catenary type shape. So you get a bit what we call a softer spring effect. Otherwise, you have the chain and the line all going at an angle like that, really stiff line with high tensions. So the heavy chain is intended to kind of soften it.
So even that piece is pretty expensive. It will actually maybe decrease the cost overall because you make the systems last long.
Precisely. Yes.
One follow-up question, quick. You mentioned that the turbine is always aligned with the wind, but
Yeah.
For the survival conditions, the turbine does no longer operate. They're stopped.
Which one? Yeah. Some of the DLCs, yes.
So what is aligning the turbine with the wind when they're stopped? Is it just the mooring system or?
Right. So it's like, yes. So the turbine is originally at 0 degrees, and then let's say it stopped due to a fault. That's one condition. Turbine rotates, it's aligned 180, and then it stopped. That's the other condition. The center of mass, the suspended mass of the nacelle is different between the two cases. So that adds some element of it.
So it's defined by the DLCs.
Yes.
Okay, yeah, thank you. That was yeah, thanks.
Thank you very much for the nice presentation. Just out of curiosity, if you try to see what happens if you don't have this heavy chain in the top and have it further in the bottom,
Yeah.
the cost, the total cost and resiliency.
Well, the reason for putting it in the top is so that the line will have a more catenary type behavior instead of like a linear spring type behavior. And so the tensions would be lower. So that's the reason we put it in the top. You don't get that benefit when it's down below.
Right, but these catenaries are expensive, right? So what if you have more synthetic rope and not having this heavy catenary, even if it's more like linear spring down?
Right. Yeah, definitely. You can go for a all synthetic type system. There are other challenges too, like when as you know, synthetic line touching the seabed creates all sorts of challenges because of sand getting into the rope and vibration.
But in this
You
case,
really don't want to contact.
yeah, but in this case, it's more likely because it's more catenary, it's more likely to touch the seabed.
Yeah, that's right. And that's something we have to watch. Like when we did the simulation, we were always looking at, does the rope touch the seabed? And as long as it doesn't, that's quite okay. So
In your simulations using the viscoelastic model, what sort of conditions did you see affected the sort of discrepancy between a non-viscoelastic model result versus the viscoelastic model result in terms of like wave frequency or things like that? Is there any patterns that you saw in terms of discrepancies?
no, we did not venture into any sort of parametric model. We only did a validation work. And the only other work which I showed was the calculating the dynamic stiffness. So, but that's a good question. Well, when does viscoelastic properties become important? That's a good question to explore. Diane and then
Krish, great talk, thank you. And you did the shallow water work, and at least primarily what we were looking at was tidal variability in the shallow water system. And I can imagine that the relative balance or relative energy between waves and tidal elevation change is going to become important, particularly in the design of these systems. And I am curious about your role of wave nonlinearities. So as the system gets shallower and you start to get steep crested, waves become skewed and asymmetric. Have you explored that or looked at the role of that?
no, not in these systems. Now, that's a good question. In the case of the tidal systems where tides are important, like the oyster farm, the wave conditions were very mild. As you know, these are interior to Maine, so the conditions were relatively benign. But then the shallow water offshore wind case, that's 50, 60 meters water where the wave nonlinearities are important. And that too, when you have hurricane conditions, extreme conditions, wave steepness and breaking are definitely issues to consider.
Thank you. And I'm sort of going out on a very thin limb as I ask this follow-up. We see evidence of momentary liquefaction as the wave asymmetry starts increasing. And I think there's been some evidence to suggest that momentary liquefaction in shallow water environments can be up to about half the wave height. I'll tell you, we don't observe that.
Sorry, liquefaction
Of the sediment bed.
The
So
sediment.
I can imagine
Okay.
it could impact the sort of anchoring systems
Right.
if you're tugging on things in a particular manner.
Now, that's a big issue. Even the anchoring systems, which I have not touched at all, no expert on it. The types of anchoring systems, very important, huge challenge. Now our DC is funding a number of studies on that with the new type of anchoring, including micropile systems and the helical anchor application of that to offshore wind is also being funded by our DC.
Thanks.
Yeah, I had a question when you were talking about the research on the synthetic lines, the newer stuff. Is there any research into the effects of ultraviolet light? I know most of this is underwater, but
Yes.
near the surface, especially the like dynamics and the other ones.
Yeah, that's true. There's a lot of UV related damage that's very important, and that has to be considered. It's not part of our research, but that's definitely been talked about as serious issue for synthetic lines for many of these systems. Very good.
Somewhat of a follow-up to that. So in your work, when you look at cyclical loading on synthetic fibers, what is the mode of failure? How are these fibers failing? Is it an endurance limit? I've read some papers, some old papers recently, it's an abrasion model. And it's a loss of material through twines interacting within the leg. And so what's your experience there?
You know the origin of this question. The history is when Dave was presenting, I gave him a real hard time. So he's saying, this is my chance. Get back. Great question. I don't have an answer to that. Honestly, I don't know.
Well, what does Orcaflex do? I mean, is it an endurance limit? But I mean, the papers I seem to read lately from the 80s, actually.
That's not lately, Kate.
The ones that I most recently have read are from the 80s.
That,
I read them last month, but they're from the 80s.
I'm not sure of how Aquaflex models rope abrasion. That's a good question. I have to go investigate it. Now, some of the papers I have seen related to that, and relevant to the other question, is most of the abrasion happens when sand grains
Sure.
get inside.
Or biofouling.
Biofouling, maybe,
Yeah.
but we
it's
don't
all
know.
sediment
We
transfer.
don't know. Some people think biofouling, maybe it's not a big deal. But when you scrape the biofouling, yes, definitely that's a big deal. But that by itself doesn't cause damage, is what you're saying. But the sand part, I've seen pictures, actual pictures presented at OTC on the line is good everywhere. The only damage is right where the sand is, and it's just abrasion. The line getting cut by the edges of the sand grains. So that's the closest I can say, but I would like to investigate.
Yeah, it was a big mystery to me when I read those older papers.
How many people here were alive in the 80s? So, but if I can follow up on that, but that would suggest that the sand issue, if it's about the sort of spherical nature of the sand grains, it's going to be a bigger issue offshore than in the near shore, where the sand grains are probably going to be more rounded and less sharp edges.
And most of the ropes they use in the industry have a protective sheet on top of it. So that helps. But the place where the sheet breaks is where the sand gets in. So that's the challenge.
Unless you're deploying a kelp farm, you go to Hamilton Marine and you get in 3-strand nylon.
Yeah,
It's, I'm glad you brought that up. That local material comment.
Okay, well, please,